Gas mixtures and partial pressures. So when it comes to gas mixtures and partial pressures, it we have to work with John Dalton's law of partial pressure. And it says, let's read the statement really quickly. It says the total pressure of gases, of a mixture of gases, equals the sum of pressures that would exert if they were present alone. Each pressure exerted by a particular component of a mixture of gases is called a partial pressure. So what does that all mean? Imagine the following. Imagine we have a gas tank right here, and we have oxygen. So oxygen is going to have its pressure, P of O2. We also have, let's say, so inside the gas, we have oxygen, we have nitrogen, we have methane. Well, the pressure of nitrogen is right there as well, and the pressure of methane. What John Dalton's law says is that the total pressure, P total, is adding up all of these partial pressures. So you would say P of N2 equals P of O2 and P of CH4. That's what John Dalton's law is saying. So you need to remember one thing here, like what it says here, is that what is going to change is the pressure for each gas based on the following, based on the number of moles, So let's say we have this equation, P total. So what's going to be different is that, let's say N of A is going to be, because we have different amounts, RT over V is going to be the same. N of PB will be the different, and then over V plus NC RT over V. I mean, think about it. The volume is not going to change, just that tank, right? You did not, each gas doesn't have its own volume. It's all in that same volume. The same thing with the temperature. You hold it at a room temperature. It's impossible to hold each gas at its own temperature. So this basically becomes like this. Na plus NB plus NC RT over V, etc. Now, when we do it this way, we can solve for problems very, very readily by calculating the P total. But we're way beyond just solving straightforwardly, right? We have to investigate more, like in this question. However, we use this equation or in one of its forms to help us solve. So let's look at this involved equation or this question, and we have to read it carefully and again understand why we're doing it this way. So it says a 255 mil gas contains, or gas sample contains argon, Ar, and nitrogen, that's N2. So you might have committed a mistake by thinking N is an N2. Remember, this is a diatomic. Go back to the list of the diatomic elements. At a temperature of 65 degrees Celsius. 65 degrees Celsius. Right away, convert to Kelvin. So 65 is in Celsius. We need it in Kelvin, and that gives us 338 Kelvin. The total pressure, so that's P total, is 725 millimeters of Hg. But the partial pressure of argon, so you say P of Ar, argon, is 231 millimeters of Hg. What is the mass of the nitrogen in the given sample? Very well. So what is this question asking you? This question is asking you to use the P total equation, which is the pressure of argon plus the pressure of nitrogen. Now, then after you calculate for the pressure of nitrogen, you can solve for the mass using the ideal gas law equation. But let's start. You do agree with me that P total is given right here. And that P of argon, the pressure of argon is given. So we plug them in to solve for the pressure of nitrogen. So P total is 725. $231 for the pressure of argon plus P of N2. So we have to solve by subtracting negative minus 231 minus 231. And this gives us Pn2 of 494 millimeters of Hg. Okay. Now it is advisable that you convert this to ATM. So right away we say P of N2 or 494, because we need as much space as we can. If we go back to one of the first few pages, again, 1 ATM is 762 millimeters of Hg, which is the same as 2R. So you divide by 760. $494 divided by 760, that gives you 0.650 ATM. Very well. So you have your pressure of nitrogen. Now, the next thing that we need to do is identify what we have. We have the pressure. We have the temperature right there. We have the volume, 0.255, or 255 mils, which is, remember, we divide by 1,000, so that's 0.255 liters. And of course, we have R because we can look it up, 0.0821. So when you get to this point, you ask yourself, well, what should I do? What do I do next? Because essentially we need to get to the grams of nitrogen. So the grams of nitrogen is what's unknown. So the grams of nitrogen is your unknown. It's X. Well, think about it. Remember, we have to use, as we said here, we have to use the ideal gas law equation. So it would be PV equals nRT. You would be solving for N because moles can be converted to grams, but first you have to find moles. So then you'd have to divide each side by RT so you can isolate it. And that would be PV over RT equals N. So let's plug in. Pressure, .650 ATM. Volume is 0.255 liters. Gas constant is 0.0821 liters ATM per mole K. And of course, the temperature is 338 Kelvin. Okay, and if we do that calculation, we get we need three significant figures, we get 0.00597 moles of N2. Now, can you take this number and convert it to grams? Yes, we can. So we take this number and multiply by the molar mass, which is 28.02. Again, this is from the periodic table, 2 nitrogen atoms. And that gives us 0.168 grams of N2. Now, once again, you can rewatch when we move forward with some of those involved problems throughout the semester. You may have to watch these videos multiple times to see what was done and why. And it actually has an advantage over being in classroom because, again, you can repeat how I did it, of course, in addition to watching other videos online. But the one message that I want to leave with you is that never ever think that you can forget what you learned at the beginning of the semester, because we're in the middle of the semester. This is stoichiometry all over again, because everything is connected. We cannot just simply talk about gases without their stoichiometries, because they're quantities. They're measured in mass, in liters, etc. So all of these are relevant here. So work through more problems in your homework, and then we'll do more when we meet next time. But bring questions with you when we meet.